right, welcome to section 10.6. This is the last section in chapter 10, and we're going to be looking at some of the uses for the combinations that we've done so far. So we're going to look at what we call a binomial distribution, and the idea of a binomial distribution is that the probabilities add up to 1 or 100%, and we're looking at the fact that we're going to give you an experiment and what are the possible outcomes for this experiment. And so that's kind of what we're doing today. So take a look. We're going to let x be a random variable that represents the sum when two four-sided dice are labeled 1, 2, 3, and 4. Okay, so what I'm going to do is I just want to, and maybe somewhere on there you want to look at what does it mean. And so I'm actually going to put that over here. What it means is I could take the sum of like 1 and 1. I could take the sum of 1 and 2, 1 and 3, 1 and 4. And then 2 and 1, 2 and 2, 2 and 3, 2 and 4. And this is kind of like the idea of rolling the die that we did before. 3 and 1, 3 and 2, 3 and 3, 3 and 4. Last one, 4 and 1, a 4 and a 2, a 4 and a 3, a 4 and a 4. Okay, and so we wanted to talk about what are the sums, and so we're going to make what we call a probability distribution table. So I'm going to make a table where x is talking about the sum, and p of x is the probability that you get that sum. Okay, so I'm going to make a table. Now as I look at my dice, what's the smallest value that I could get for the sum? It's when I take 1 and 1, and 1 plus 1 is 2. So my smallest sum is 2. And then I go to my next diagonal, 1 and 2 and 2 and 1, that means I could have a sum of 3. And I could have a sum of 4, 5, 6, 7, there's 7. My last sum has to be 8, 4, and a 4. And so what I want to do is look at the probability that that occurs. Now, how many outcomes do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have 16 possible outcomes for my sum. And so as I look at this, then I want to talk about the probability. Now, what's the probability that I get a sum of 2? Well, there's only one way out of the 16 outcomes, so it's 1/16. What's the probability that I get a sum of 3? Well, I could have 2 and 1 and 1 and 2, so there are 2 possibilities out of the 16. Now, we always reduce our probability, so 2 out of 16 is the same thing as 1/8. So I do, what's the probability that I get 4? Well, 1, 2, and 3. 3 out of 16 doesn't reduce, so we leave it as 3 out of 16. What's the probability I get a sum of 5? 1, 2, 3, 4. 4 out of 16 reduces to 1/4. What's the probability I get a 6? Well, 1, 2, and 3. 3 out of 16 we said doesn't reduce. Probability I get a 7 is 2 out of 16, or 1/8. Probability I get an 8 is just 1 out of the 16. And so this is called our distribution table. Is what I basically look at is what outcome could I have and what's the probability that that outcome occurs. Now what I'm going to do is make what we call a histogram, or what you know it more as is a bar graph. And so I look at this bar graph. Now I'm going to put the sums on this side. Well, I had a lowest sum of 2, then I could have a 3, 4, 5, 6, 7, and an 8 were my possibilities. And so the sum of the two dice was what we called the x. Probability we called p of x. And I want to label kind of each line. Now I know my smallest possibility was 1/16. And then I had, for the sum of 3, I had 2/16, which we reduced. And then 3/16, and 4/16, and 5/16. And so I'm going to label my bar graph that way because I think that tends to be the easiest. And so what I'm going to do is put a bar for every sum. So at 2, we only had a probability of 1/16. At 3, we had a probability of 1/8, which was 2/16. So I go up to 2/16. At 4, our probability was 3/16. At 5, 1/4 was the same thing as when we reduced 4/16. At 6 goes back to 3/16. 7 goes back to 2/16, 8 goes back to 1/16. And so we're looking at this bar graph. Now what I want to talk about this bar graph or this histogram is the idea of what we call either symmetric or skewed in look. And in this case, this is a symmetric set of data because if you'll notice, if I put kind of like this line down the middle, it's the same thing on either side. And so it's got symmetry to it. And so that's what we're talking about. This is a symmetric histogram, okay, or a symmetric set of data. And I kind of want you to keep that in mind. If it looks the same on either side, if you cut it kind of right down the middle, then it's considered symmetric. Now looking at my bar graph, what is the most likely sum? Well, which is the highest number in our bar graph? As you look at this, the most likely sum is to get a 5. Now we want to know in D, what's the probability that your sum is at most 4? What that means is take the probability of 0, probability of 1. Let's try with 0. Should we try again? Because that doesn't work, right? What's our lowest sum? Our lowest sum is 2, and then we could have had a 3 or a probability of getting a 4, and I apologize for that. So I could have had a sum of 2, 3, and 4. So I'm going to add those probabilities together. And I'm going to put them back as 16ths. 1/16 plus 2/16 plus 3/16. 1 plus 2 plus 3 is 6/16. But that can reduce to 3/8. So the probability that it's at most 4, so it has a sum of 2, 3, or 4, it's basically saying let's add these pieces together. You take your fraction and then don't forget we always reduce a probability. And so this is the first idea, is I think it's best in order to do this to list your outcomes, then make your table, then draw your histogram, then start answering the questions that we give you. Now this is great when they actually give you something that you can write down in a decent, timely fashion. We're going to show you this next one though where it's not quite the same. A binomial experiment has this idea where I am working with all of these n independent trials. Okay, that means when I do my first trial, it won't affect what happens in my second trial, which won't affect what happens in my third trial. Now, when we do these binomial experiments, here's the idea. You either get a successful experiment or you actually fail in your experiment. So and it doesn't mean like you either pass or fail. What it means is you get the outcome you want or you don't, okay? The probability of success will be the same no matter what trial you do. And they're talking in terms of trials like flipping a coin or rolling a die or guessing on multiple choice exams, things like that. Success we denote by a P, and failure is the complement. It either is a success or it's not, and we do the complement with 1 minus the probability of success. Now they're going to give you this equation. This is the only equation I will give you on the test. This is it. The way we say k successes is we look like this. And it kind of goes back to like the binomial expansion. I take n combinations of k successes. So out of my trials in n, however many trials I have, k of them are considered a success. I multiply the probability of success to the kth power because I'm looking for k successes with that percentage rate. And then I do my number of failures, 1 minus p, to however many other trials there are. And we say n minus k. And I'll show you a couple examples of this, but this is the only time I'm going to give you this formula. Again, P talks about your successes. 1 minus P talks about your failures. And I want to kind of show you what it looks like. And I'm going to do 2 questions with you because I want you to see it. And then we're going to kind of look more in general terms. We are looking at, in example 1, the probability that you toss a coin 20 times and you only get 2 of the hats. Okay, so this 2 is my success. This is how many successes I want. And so what we say as we look at this is out of the 20 trials, I want 2 to be successful. Now when you flip a coin, Heads is what I want my success to be. So what's the probability that you get a heads? Well, because there's one side that's heads out of the two sides, my probability of getting a heads is 1/2. Okay, and I want 2 heads, so I raise that to the 2nd power. Now I'm going to multiply that by the probability that I don't get a heads, which basically means what's the probability then that I get a tails? Because those are my only 2 options. Well, there's only 1 tails out of the 2 sides, so it's 1/2. If 2 of them are heads out of the 20, then 18, the other remaining 18 have to end in a tails. What I do then is I stick this in my calculator. 20C2 times 1/2 squared, please use the parentheses, times 1/2 to the 18th. What you get in your calculator says this, 1.812 times 10 to the -4. Please make sure you can actually get that. And we don't want you to leave it in scientific notation. This -4 means take this decimal and move it left 4. I end up getting the decimal point 0.001812. And so this says the probability that I end up getting 2 heads out of my 20 coin flips is like 0.0, if I move it back 2 places for percent, it is basically saying 0.01812%. So not even 100th, I mean, you're looking at about 100th of a percent, which is not very good odds. Okay, so this is the idea. So let's try a different one with a different success and failure rate. We're going we want to guess 6 answers on a 30-question multiple choice exam, okay? And they're giving you that you have 4 options for your multiple choice. So I'm going to start by, out of the 30 questions, I want 6 to be correctly answered. Not very good. I'm not aiming for much, but here's the idea. Now, what's the probability on multiple choice that I get the correct answer? Well, only one of these 4 numbers are going to be, or letters are going to be correct. So it's 1/4 that it's correct. And because I want 6 of them to be the correct, I raise it to the 6th power. Well, if only one of them is correct, how many of them are wrong? 3/4 of them are wrong. And what that means is if 6 out of the 30 are correct, I'd have 24 questions that aren't correct. So again, I'm going to stick this in my calculator. Again, parentheses you need. I end up getting about 0.1455. And if I wanted, I could change this to a percent, which means I'm about 14.55% chance of getting 6 of them right. And so that's kind of one way to look at it. Now again, I'm going to give you that formula. That's the only one I'm giving you though. And I want to show you one more experiment. So on the back of your frame is a different type of notes. And so let me get there with you. Okay. And I've got to do a little bit of work a second to make sure I'm there with you. All right, I'm good. Let's take a look at this. What this says, I can get rid of this. What this says is we're going to make a distribution for a story problem that they give you. Okay, so a survey found that 68% of the students are not afraid to fly. 68% is what we're looking at. Okay, this is what we consider our success. So students who aren't afraid to fly, we're going to say 68%, we're going to always put it as a decimal, 0.68. Okay, now, suppose you randomly survey 5 students. Draw the histogram distribution as we look at this. Okay, now, I want to do it this way. They consider Q the failure, and that's one of the things your book does, which is just 1 minus P. So 1 minus 0.68 would end up being 0.32%, 32%, and that's going to be our failure. So our success is P, our failure is Q. Now, how many students are we working with? We're working with 5 students, so we're going to make our number of trials 5. Now, the problem is I don't want to have to write 5 different equations. So what I can do is put this in my calculator. And I'm going to go into my y equals menu, and here's what I'm going to start with. 5 combinations of x, and I'm going to make x anywhere from 0, 1, 2, 3, 4, and 5, and I'm going to let my table do that for me. Then I multiply it by my success, which is 0.68, and we want x to be our successes so it can put it in for us in our table. And then we do our failure, which is 0.32, and together the x and the failure has to equal 5. And so the way we put it, you'll need a parentheses, 5 minus x. Now this is not something I'm going to give you. I'm only going to give you the general formula, and you're going to have to figure it out. So we're going to be practicing another one of these in class, the one that's on the bottom for you, but I just want to kind of give you an idea. So what you would do is now go to your table after you put this in. And what you're going to do is at your table, they're going to give you a decimal. Now the way it would look if I did it by hand, let's say I don't have a graphing calculator, is I would take 5C0 times 0.68 to the 0 and 0.32 to the 5, because again, these two together have to equal the number of trials you're doing. If I have a graphing calculator, you should be able to see it's like 0.003. Okay, but again, if I don't have a calculator, I can make this work. If I want one success, then I say 5C1 times 0.68 to the first 0.32. If one is a success, then there are 4 failures, because together it adds up to 5. You get 0.036. Now to save us some time, I'm going to help fill these in for you. 0.322, 0.342, and 0.145. And this is what your graphing calculator would give you. Again, if you don't have the grapher, we're at least giving you the equation to make sure you can do that. Now, we did this as x is the number of students who are not afraid to fly, and the probability of x, if we were to make, this is kind of our table, where here's our x, and here's our probability of x. Now, you'll notice these don't go up in nice numbers like our last one did, so we got to kind of figure out how to make this work. It looks like I need to go up to 0.4. And so here's what I'm going to do. I'm going to make this 0.1, 0.2, 0.3, 0.4. And I kind of look at what my max needs to be, and it evenly works out to do it that way. So this means this is 0.05, 0.15, 0.25, and 0.35. And I'm just trying to get equal increments. You cannot, let me just put it this way, you cannot just put each of those numbers here along this left-hand side and think it's going to be okay. It has to go up in equal increments. We know that we started with 0, 1, 2, 3, 4, and went up to 5 people. So those are our x values. And so if I look at 0.003, that's going to be like way down here. So you're not really going to have a whole lot, right? At 1 student is 0.03. So 0.025 would be here. So 0.03. At 2 is 0.152. So 2.15 just above that. 3 is 0.322. So 325 would be kind of halfway in the middle, so right there. Number 4 is 0.342, so up to about 0.35. And last but not least, 5 is 0.145, so right down kind of here back by the 0.15. And so you're making a table as you go through. Now, you can look at this both in table form and in data form, but take a look. What is the most likely outcome? Well, obviously, I think from a histogram, it's easier to see that 4 students not being able to, or not being afraid to fly is the most likely. Now, I do want to say students, because at least we know what I'm talking about, right? What's the probability that at least 3 students? So that means take the probability of 3 and the probability of 4 and the probability of 5 and add them together. And so you end up getting, let's do that, 0.322 plus 0.342 plus 0.145 equals 0.809. What that means percentage-wise, and you should know kind of what this means, percentage-wise, it means about 80.9% of students, or 80.9% happens when 3 or more students aren't afraid to fly. Okay? Now in this case, is my histogram or my data symmetric? And we said it was symmetric if you could draw kind of this line down the middle and you would get the same thing on either side. I think it's pretty obvious that this is not symmetric. And so what this is called when the data is not symmetric is a skewed set of data. And skewed just means it's heavily pushed in one direction. So in this way, you can see there are more people that are not afraid to fly than there are afraid to fly. And so that's kind of what we're looking at. So this is the idea that our data is skewed. And what we're going to do when we get to class is do the bottom example to make sure that I can answer for you how to put it in your calculator and how to use the formula if you don't have a grapher and things like that. So this is the end of section 10.6, and again, basically the end of chapter 10. Please know again, I will give you the binomial distribution equation, the one that kind of looks like this in general forms, but that's the only thing that I'm going to be giving you. So that's it for 10.6. Thanks for watching.